Welcome back. In the previous lecture, we had seen compact subsets of the space of continuous functions, uh, which is the theorem called as Collier-Zela results. And now, today, we are going to look at compact subsets of LP-Rn. This is what is called the Kolmogorov criterion, Kolmogorov compactness criterion. This is a very special case of general case that we already know, which is that in the metric spaces, compactness is equivalent to closed and total boundedness. So these results are kind of gives a different uh, way of different way of getting the total boundedness of subsets in these spaces. Okay, so let's go to the Kolmogorov compactness criterion. So this theorem actually tells you that if you take LP-Rn, so this is for Rn because the proof involves convolution of function, and we have discussed about convolution already, which is meaningful only in the entire space Rn. So for any p which is not including infinity, p from 1 to infinity where infinity is not included, if you consider LP of Rn, and if A is a subset of LP of Rn, then A is relatively compact in LP of Rn if and only if these three conditions are satisfied, which is that A is bounded, then limit of r going to infinity, integral outside a ball of radius r as r goes to infinity. So this integral is 0, and this happens for all f in A uniformly. And the third condition is that this LP norm as h goes to 0 is 0 for all f in again uniformly in A, where this tau h of f is precisely the translation by h variable by the h vector. So if you remember the definition of convolution, we had this translation in the definition of convolution, right? So just for simplicity, I have introduced this notation here. That's it. So we say a set is relatively compact. So here you see um, we also need an assumption of closed set, right? I mean closed. The set be closed. So instead of that, I have just said it's relatively compact. So if you take the closure, it becomes compact. So so is so a set A is relatively compact if and only if these three conditions are satisfied, and that's what we are going to prove. Okay, so we are mostly interested in the sufficiency condition. Then the necessary condition is actually kind of easy to do. Okay, so let's start with let's just do the sufficiency condition, which means that we need to assume that 1, 2 and 3, these three conditions hold, and that implies the compactness of the relative compactness of A. Okay, so to prove that A is compact, what we need to, that is A is pre-compact, right? Because we are not, that is closure is compact. What we need to show is that for any epsilon, you can find a finite number of balls which cover A, right? Centered at F1, F2, Fa. Basically, you can get K elements from the set A, such that if you take an epsilon ball around all these elements, then that covers A. This is what we need to show for compactness. So A can be written as finite union of epsilon balls, right? So to prove this, let's choose an epsilon greater than 0, right? We need to do this for every epsilon, right? For each epsilon we need to show for any epsilon. So you start with an epsilon, then by the condition 2, which is that integral condition outside, which is this condition number 2 here, which is that r goes to infinity, this integral is 0 for all f in A. So from this condition, there is an r, because it goes to 0 as r goes to infinity. So you can choose a r big enough such that this integral is less than epsilon, because this goes to 0. So you can choose an r big enough such that this integral is less than epsilon, and this is true for all f in A, right? Because the convergence was uniform with respect to elements of capital A. We have already seen in when we dealt with the regularization and cutoff techniques and so on, we have already introduced the notion of modifiers, right? And we said that if you convolve with modifiers, you can actually smoothen out a function. So that's the idea of the proof. So the proof involves this idea. Precisely, we have the compact sets characterization for the space of continuous functions, right? So you take any LP function, you convolve with the modifiers. So you actually go and sit inside the space of continuous functions. Then you look at the corresponding set in that space. Then use the compactness there, and just show that whatever conditions we have assumed here for LP spaces, uh, when you restrict to when you go via convolution into the space of continuous functions, the compact subset criterion is satisfied there, and that is how you get the compactness in LP spaces here. That's the idea of this theorem. So we have these modifiers, and we have shown that they are dense, right? So there is some kind of density result. If you remember the theorem 34, which is this, that Cc infinity of omega is dense in LP of omega. We have this density. So if I take an element here, I can get a sequence in this space which will converge in the LP norm, right? This is a proof that we have seen in some 2 lectures before, right? When we did the regularization and cutoff technique. Okay, so we are just using that density property. Yeah, yeah. So from that density result, we have that for all n, we have this property. So you look at f minus f convolved with rho n, that the p norm. This by definition, so like the same idea that we did when we did the regularization and cutoff technique, that you have an f here, you write this in the integral form. Now you know that the integral of rho n is 1, so you introduce that here, and you will have with convolution here, you take the one that common here, so this estimate, so you get this estimate here. Okay, and now what you do, because this integral is 1, you take supremum over all y, right? Because this is over y, and this has a support of 1 over n, right? Rho n has a support of 1 over n, so you take supremum for all y within that support of rho n, which is within a ball of radius 1 over n. So you take that, so this integral is 1, so what you get is this inequality here. So you start with any f in A, so for every f in A, you have this property that f minus f convolution rho n is this. Okay, where this supremum is over a ball of radius 1 over n. Now the third condition in the statement, which tells you that tau h f minus f, this goes to 0 as h goes to 0, right? This condition, you use this condition. Now you use that condition. So you are here, if you actually see, this f convolution rho n is actually sorry, this one. So this f minus f convolution rho is less than or equal to this, and f minus tau y, this goes to 0 as mod y goes to 0, right? So you can actually get an integer n epsilon. So given the epsilon, you can get an integer which depends only on epsilon. You can get a number, natural positive integer, such that for all f in A, this is less than epsilon, right? Because this can be made less than epsilon, so this is less than epsilon for n epsilon. This is by the condition hypothesis 3 that we had. Okay, so given f, for every f in A, one can obtain an n epsilon such that f minus f convolved rho n epsilon, LP norm of that is less than epsilon. Okay. Okay. Now what you do is that observe this property that for any f in LP of Rn, we have this inequality. So basically f star of rho n minus evaluated at x and f star of rho n evaluated at z, right? This so the difference between them is less than or equal to this. By definition is integral over this, right? Because there's a convolution with rho n. So there's a translation of the f variable here, and this is precisely by the Hölder's inequality. By the Hölder's inequality, this is this inequality where this f check basically means f check of x is f of minus x. Okay, so this is just that. So you have x minus y. So f of x minus y is nothing but f check of y minus x. So f check, as I said, is f check of x is f of minus x. So you can take minus here, so you'll get minus of y minus x, which is nothing but f check of y minus x, and that is nothing but translation by x of y, so tau x of f check. Similarly, this is minus tau z of f check. So by the Hölder's inequality, this is norm p of this and norm q of this. And this last inequality you obtain by the fact that I have missed saying a translation. So this is by the translation invariance of the Lebesgue measure, right? So this Lebesgue measure has this translation invariance property, right? So this is from that, this is precisely from that. So this, so from here we can write it like this. So the tau x minus zf is minus f. Now this, in fact, this is just the Hölder's inequality, right? If you don't have to, if you just take one term here, you are going to get this thing. So the proof of this is same as this. This is whatever we do here is what we have done here as well, right? So this is by the Hölder's inequality, nothing else. Okay. So if you remember something like I had talked about Young's inequality and so on when we define convolution. Okay, so now what we do is that now we have checked some properties. So for every f in here we have all these properties. So now slowly what we do, if we take any f in LP, if I convolve it with the modifiers, I already said it moves into the space of continuous functions. But now space of continuous functions on Rn, right? But if you have to use a result like Ascoli-Arzela, we need a domain to be compact set. But we know that the modifiers are supported on a compact set. So you look at the support of the modifiers. So if f is an LP, f convolved with rho n can be seen as a map from a ball of radius r in Rn centered at 0 to R. So for all f in capital A that we started with in the statement of the theorem, you define script A, which is this class of functions that is corresponding to each f in capital A. You convolve with its modifiers. Now that's a function from BR0 to R, and you can quickly verify that the script, so the script A is actually a subset of the space of all continuous functions defined on BR0. Okay, and by the conditions 1, that is that this capital A is bounded, and that LP norm of translation minus f that goes to 0 uniformly for all elements of A, that, and the Ascoli-Arzela result, because that is going to give you the equicontinuity. You already have boundedness and so on. So by the Ascoli-Arzela result, the script A is relatively compact in CBR0 in the uniform topology. Okay, so if script A is relatively compact, means it can be covered by finite number of balls, which basically means that there is a finite set of elements in the capital A such that its corresponding element in script A, which are Fi convolved with rho and epsilon. If you look at balls, you can get a ball of some radius such that they are A is contained in the finite union of those balls. I mean, all those balls, right, centered at this point and some radius. Now, what you do is that your your epsilon is fixed, right? So you choose your radius here such that, I mean, this is for later, this is just so you will get some radius. If you don't choose it like this, if you just, then later you are going to get some factor when we prove. So this is like when we do the estimates, we choose epsilon by 2 and epsilon by 3 a priori, so that finally we get an epsilon, right? So this is only that you will see why we have done this. So if you actually, just to give you an idea, this 1 over p is coming because of the LP norm. So when you take the LP norm, there is a P and 1 over P, right? So to accommodate for that, this N is coming due to the dimension. We are working in the Rn space, right? So the volume of the ball will involve a dimension N. So this N is coming because of that. You will see later when we do the proof how this and why this choice of factor is natural. Okay, so by the Ascoli-Arzello theorem, the script A can be put in finite union of balls centered at these points. Okay, so now for all f in capital A, we can choose, right, by that definition, which means that for any element of script A, uh, any element of script A is sitting in one of the balls here, right? So the difference of that element from this wherever it sits, for some I it will be contained in that ball, so it will be less than this radius, right? So this is what we are saying here. So for all f in capital A, but we are saying it in the not, we are just converting whatever we said for script A for the capital A form, right? Because the relation between script A and capital A is that you take any element of capital A, convolve it with rho and epsilon, that is an element of script A. So you now have a property of script A which is contained in the finite union of balls. So for all f in capital A, there is some j from 1 to k, one of the j, such that for all x in this ball of radius r, f minus fj is less than or equal to this. Okay, this happens. This is precisely from this condition, because any element here is of this form, right? So f star rho and epsilon minus fi rho and epsilon is less than epsilon r minus 1 over p and so on, right? That's it. So that's what we are saying here. And the n is missing here because this br0 absorbs that dimension n here. So if you compute the volume of br0, that n will appear. Okay. Okay. So now if you look at the difference f minus, so for any f you can pick a j like this. Now for that j, you look at f minus fj, right? And look at the LP norm of that. In this, what you do, you add and subtract f star rho and epsilon. So f star rho epsilon is subtracted here, so it's added here, and then fj of rho, fj convolved with rho and epsilon is subtracted here and added here. Okay, so both are done. So that is done, and then you apply triangle inequality. So you get 1, 2, 3 terms here. Now in the third term, if you see, third term, all these terms are this integral, this norm is computed in Rn. So you get 3 terms here after adding and subtracting, but this third term you are having it in Rn, so you split it into its split it into the support, split it into the ball br0 that we already chose it, right? we already did that BR0, right? Where did we do? Here. We chose an R here, right? Such that this is less than epsilon outside the ball, right? That R, right? So you restrict this function to that ball of radius R, and then outside that you will have the same quantity in the outside the ball, right? That quantity becomes these two sum. If you write it down properly and evaluate, because it's normal, you see you have rho and epsilon here outside the thing. After some stage this has not much support, so what you will be left is just f minus fj over this region, which by again the Cauchy-Schwarz or Wrangle inequality or Minkowski's inequality, you get this term here, right? So you start with this, add and subtract these two terms, and the third term you split them between two domains, BR0 and the complement of BR0. The complement of BR0 is less than or equal to the sum of these two terms. So you have these 5 terms here, 1, 2, 3, 4, 5, right? 5 terms here. So this quantity is less than this. Now here if you see that the way we had chosen, the first two terms are less than epsilon. That is how we chose the R. The R was chosen such that this is less than epsilon for all f in A, right? So f is also in A and fj is also in A. So the first two terms are anyway less than epsilon. Similarly, this is also so the third and fourth term is also less than epsilon from what we did here, right? We chose our n epsilon such that f minus f star is of rho n epsilon is less than epsilon for all f in A. So both f and fj is in capital A. So this estimate is true. So the third and fourth term is also less than epsilon. Okay, third and fourth term is also less than epsilon. Now what remains is the fifth term. The fifth term also, you see, we have shown something here in the whenever x is in the ball. That is why we had split this for the ball. So whenever x belongs to BR0, you actually have this estimate. So the fifth term actually satisfies this. So let's look at fifth term. So fifth term LP norm is precisely this, which by whatever we have shown here is epsilon BR0 minus 1 over P. And what once you take that number outside this integral, what is left is integral over BR0, which is just the volume of the LP norm of that ball, which is BR0 1 over P. There is a minus 1 over P here. That is how we chose the radius there. So that cancel out, what you get is epsilon. So this term, so the way we chose this ball there, not this radius here, is to compensate for is to make sure that we get an epsilon here. So what we have shown here is that f minus fj LP norm is less than or equal to 5 epsilon. Okay, so I could have started with everywhere with an epsilon over 5, then we could have just got epsilon here, whatever. So this is what we need to prove, that you start with an f, you have a finite number of points fj such that uh, f is in the ball centered at fj of radius 5 epsilon. This, which means that A is contained in a finite union of balls centered at fj, which means that A is pre-compact or relatively pre-compact. Okay, so this is what we wanted to prove for. So this is the compactness criterion for LPRN. Okay, so this we will stop. We'll meet in the future lecture. Thanks a lot.